Hey everyone, welcome back and let's write some more Leetcode today. So today let's solve the problem combinations. We're given two integers, n and k, and we want to return all possible combinations of size k, each combination has to be of size k, from the range 1 through n. So these are all the numbers that we're given, 1 through n, and we want to create all possible combinations from this set of numbers where each combination is of size k. And we can return the solution in any order because yes, it's going to be a pretty large solution depending on the input parameters. And basically, since we're told to do all possible combinations, we really have no choice but to do the brute force solution, right? We actually have to create each of these combinations. So yes, it's going to be brute force. And when you think of brute force, what do you think of? Well, you should think of, recursion or DFS or specifically backtracking. So we're going to have to, generate every single combination from this set. So let's just take a look at this example. We're given n equals 4. That means we have 4 numbers, right? 1, 2, 3, 4. And we want to create all combinations from this set of numbers that's size 2, right? Each combination has to be of size 2. So like I said, brute force backtracking is usually done with a decision tree, right? So we want to create combinations. What's our decision going to be? Well, one decision could be we want to create every possible combination, including a 1 value, right? So we have a 1. And okay, so we have a 1, right? We already chose a 1. Now we have these 3 numbers to choose from, right? So we can make 3 decisions in the next choice, right? So 3 decisions, we can either choose a 2, we can choose a 3, or we can choose a 4. Now at this point, let's say starting from 2, right? Here we have 2 values, 1 and 2. Now are we going to make another choice? I mean, we could choose a 3, right? We haven't chosen that yet. We've chosen these 2. We can choose a 3 or we can choose a 4, but we're going to stop here. Why are we stopping? Because look at the numbers that we have. We have 2 numbers and that's what we wanted, right? K equals 2. We just want combinations of size 2. So basically what we've discovered is that for this decision tree, the height is going to be K, right? That's going to be the height of the decision tree. We're never going to go lower than that. There's no need to go any lower than that. So far here, we've created 3 combinations, 1, 2, 1, 3, and 1, 4. You can see that those 3 are down here. And so from the root of the decision tree, how many other decisions could we possibly make? Well, of course, we could have chosen a 2, right? We could choose all combinations starting with a 2. Okay, so let's say we did choose a 2. Then, we've eliminated this choice. Then what else can we do? Do we have 3 decisions from here? Can we choose a 1, a 3, or a 4, right? Because look at those are the values available to us, aren't they? Well, if we do choose a 1, don't we get the exact same combination that we already got? 2, 1. A combination is not a permutation, right? 2, 1 is the exact same as 1, 2. They're the exact same combination. We're not looking for permutations where the order actually matters. So these are technically the exact same combination, so we don't want duplicates in the result, right? You can see that 1, 2 is here. We don't want 2, 1 in the result. So we don't want duplicates. How can we eliminate that? It's pretty easy. If we, from here, right, we chose a 2. So, in our array, we chose a 2. If we choose a 2, we only want to, following decisions that we make, we only want to choose values that are greater than that 2 or whatever value we ended up choosing, right? We only want to choose greater values. We don't want to go back to the left because we know that we've already done that work before. So that's the easy way to do it. So from here, from 2, we could choose a 3 or we could choose a 4. The other root decisions that we could make would be starting with a 3, in which case we can choose a 4. If we start with a 4, there aren't any choices available to us, right? So we don't get anything here. So, that's not a combination. So when you actually look, remember these 3 were these 3 combinations. 2, 3, 2, 4 are up here, or 2, 4 and 2, 3. And then 3, 4 is the last combination. So we did generate all 6 combinations. Now, roughly speaking, what is the time complexity of this decision tree? You can see that at most we could make n decisions, right? At the root, we're making 4 decisions. Here, we're making 3, 2, 1. So what's the time complexity? Well, n is going to be the base value, and it's going to be raised to the power of k because k is the height of the tree, right? So this is the upper bound of the time complexity. It's not a very tight bound, though, as you might be able to tell from looking at the tree, right? It's never actually going to be this big. And actually in the code, we're going to end up every time we, create a combination, we're going to have to clone it. So the time complexity would be something like this, bounded, like the upper bound k, which is going to be the size of the combination. So roughly this is the upper bound of the time complexity. There is a more tight bound. I think the tight bound is something like n to the power, or n factorial, n minus k factorial, and k factorial. This is basically the number of combinations that are possible. This is the size of the combination, so that's where I'm getting this tight bound from, but I doubt they'd ask you for this in an interview. This is just the mathematical formula for the number of combinations we could create given this criteria n and k. But that's really it for the explanation. I hope this makes sense. The code is not going to be too difficult, so let's jump into that now. So remember, we're doing this recursively, but we are going to maintain a variable result, which is going to be a list, all the combinations that we can create. It's basically going to be global for us because in this function combined, we're going to create another function called backtrack, so where this variable and these two variables will be available inside of this function even if we don't pass them in as parameters. So two parameters that we are going to pass in, though, is this starting value that we're at, right? Because remember, when we do the recursive backtracking, as I showed in the decision tree, we want to remember which value we started at because then we can only choose values that come after it. The other that we're going to maintain is the current combination that we have, because as we go down the decision tree, we want to know what previous values did we actually add. Now, let's think about the base case here. When are we going to stop the backtracking? Remember, it's only going to be of height k. So if our combination, right, the length of that combination, the size of the combination, whatever you want to say, is equal to k, that means we can stop, right? We don't want to add any additional elements to it. So this is the base case. What are we going to do in the base case? Well, we're going to update our result, right? We're going to take this combination. We found a combination. We're going to append it to the result, right? But since this is an object, combination or list, right? This is going to be a list, is an object. We are going to continue to modify it in other recursive calls. So we don't want to end up modifying it after we've already added it to the result. So before we add it to the result, we're going to, instead of adding it to the result, we're going to add a copy of it to the result so that later, if we actually update combination, it won't update the one that we actually added to the result. And then after that, we can go ahead and return. Next, we're going to go ahead and make our decisions, right? So what decisions are we going to make? Remember, we can start at any value. So I is going to be the value that we're choosing. And we can go through any value from start, right? Start is going to tell us where we're allowed to start from. And we can go all the way up until n, right? Including n. So in Python, the second value is non-inclusive. So we're going to say n plus 1 because this is basically going to make sure that I iterates from start all the way to n, including n, but not including n plus 1. Okay, so once we have that, so I is the value that we're choosing, right? So when we're choosing it, what we're saying is we're adding it to the current combination. So we're going to add it to the current combination. Then what are we going to do? We're going to recursively run backtrack, right? We're going to continue to add values until we've added exactly k values. So what are we going to pass in for start? Right, we just chose the value I, so what value are we next are we gonna be allowed to start at? Start plus 1, or not start plus 1, I plus 1, right? We can only choose values that are greater than I, so we're gonna say the starting value is gonna be I plus 1. And for the combination, we're just gonna pass in the combination, right? It's gonna be a list. And once that is done, we want to clean up, right? We want to, we made one decision where we chose I. Next, we want to choose the next value that goes in this range, right? So we want to remove the value that we just added before we add the next one. So we'll just pop whatever the most recent value was, not poo, pop. Yeah, so this is going to be the decision tree layer, right? This for loop is basically the decision tree. And next, we're basically done, right? So we can actually just return out of this backtracking. We don't have to return. Python will return by default. So when we're done with that, we have to make sure we actually call that backtracking function that we just wrote. So what are we going to pass in for start? Not 0, but we're going to start at 1, right? Because in the description of the problem, they say we can choose values between 1 through n. So that's going to be the starting value. And the starting combination is just going to be an empty list, right? It's initially going to be empty. We're going to add some values to it and then add those combinations to the result. That's about it, right? So that's it. We call backtracking. When we're done with that, all we have to do is return the result that we make sure to update from within the function. So that's the entire code. Let me run it to make sure that it works. And even though, yes, the time complexity isn't that great, it is exponential. It's about as good as you can get, so it still runs pretty efficiently relative to Leetcode. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot. Consider checking out my Patreon where you can further support the channel, and hopefully I'll see you pretty soon. Thanks for watching.